Hi everyone, welcome to this episode of Keipert Labs. In this video we're going to be talking about the Lowry-Bronsted theory of acids and bases. So some of what we're going to go through some definitions of an acid and a base, with a little bit of recapping some of the previous theories that we've talked about. We're going to look at what a Lowry-Bronsted acid-base reaction looks like. So we're going to talk about what is an acid and a base. We're going to talk about how they react. Introduce this term conjugate pairs, conjugate acid-base pairs, and then we're going to look at this idea that some substances, we give this name amphiprotic. Okay, so let's start off with some definitions. Okay, so we're saying so far we've talked about, briefly we've mentioned about Lavoisier and his theory that acids were compounds formed from compounds of nonmetals with oxygen, that when they were put in water, which had some basis in truth, but it ignored a whole bunch of other examples that we could come across. Then Davy took that definition one step further to actually then say that it was acids contained hydrogen, which was a little too broad. And then we had Arrhenius in around the late 1800s proposing the idea that an acid was something that produced hydrogen ions in water, and a base was something that produced hydroxide ions in water. And so now we arrive in the early 1920s. Okay, so just giving you a bit of historical context to remember that we've made discoveries about things like the proton, the electron, the existence of the nucleus of an atom, concepts of electron shells, that the Bohr model was almost 10 years old by this point. We'd discovered ideas about quantum mechanics and so on. So there was a whole lot more that was understood about the atom than Arrhenius had to work with, over 2 decades before. And so Lowry and Bronsted separately, but at the same time, developed this idea that an acid, rather than producing hydrogen ions in water, was something that could donate a proton, which was a hydrogen ion. Okay, so that is a proton donor. So an acid is a proton donor, something that is able to donate a proton, an H+ ion, to something else. And that something else is a base. So that is a proton acceptor. So any substance that is able to accept a proton given by an acid. Okay, so that's kind of the definitions that we're working with here in this theory. And so, so we'll talk about what an acid-base reaction looks like with this in a second. But so this idea being that it kind of frees things up for us to not require water for the reaction to be happening. Okay, so anything that can donate a proton is an acid. Anything that can accept a proton is a base. Alright, so then that means if we're looking at, we're thinking about acid-base reactions. Okay, that because an acid is something that's donating a proton, and a base is something that accepts, acid-base reactions in this theory of acids and bases are also often known as proton transfer reactions, because they involve the transfer of one proton from one substance to another. Okay, so that's often how they're referred to. Okay, so proton transfer reactions. Alright, so I'll give you a couple of quick examples. Okay, so let's say that we've got a hydronium ion, which we met in one of our recent videos, and a hydroxide ion. Okay, so what happens is that that this hydronium ion, remember, looks like this. Okay, so it's got 3 hydrogens connected to this oxygen. It's positively charged overall because we have 3 connections to this oxygen. Okay, and so what happens is that, if I take that away for a second, we have our OH over here. Okay, so what we see in this particular situation is that one of these protons, the extra proton that is only attached by a coordinate covalent bond, is given or transferred to this oxygen. So it moves from here to here, we make a new connection and sever the old one. And so what we end up with is two water molecules. So looking like this and like this, with our lone pairs of electrons. Okay, so what we've done is we've transferred a proton from an acid to a base. Okay, let's have a look at some other examples. Okay, let's look at this one. So this is, if you remember, is acetic acid or ethanoic acid. Okay, and so what happens is that it's this proton here that is going to get moved, and it moves from here to there, so we end up with the acetate ion being left behind and water forming on the other side. Okay, so what we see in each of these situations that we're transferring a proton from one substance to another. Okay, so this is our acid and this is our base. Okay, so it always is given from acid to base. No matter which way around, whether you write them on left and right, doesn't matter. Okay, the other thing that I want you to take note of, because it's going to pop back up again when we look at these in some more detail, is that you always, in a Lowry-Bronsted acid-base reaction, you always have four things, two pairs. A pair here and a pair here. Okay, now what happens when we're thinking about a Lowry-Bronsted acid-base reaction? What we tend to think about, if I kind of clean this up a little bit, okay, is we tend to think about substances in pairs from one side to the other. So at the moment, we're going to discuss this idea of conjugate acid-base pairs. Okay, so what we see is that if we look at this as, let's think about it as a reaction of a before and after. This is before, these two things, and this is after. Okay, that's the concept of an equation. But let's look at it in terms of pairs of related substances, before and after. So let's say I'm going to look at this one. Okay, and I'm going to look at something which is very closely related to it, which is this one, before and after. So this is before the transfer, and this is the after. The only thing that's different is the removal, in this case, or the donating of one proton. One proton difference. Okay? So what we say is that these two things are linked. They are a pair. Now, they are not a pair of identical things, because obviously they aren't. But we say that these two things are a conjugate acid-base pair. So that is, they're related. They're not identical. Okay, but we have a difference of one proton. Okay, so they're related to each other. They're not identical, so it's not the same substance on both sides, but there's only a difference of one proton between them. Okay, so the proton here and here. Likewise, we can also consider these two as to be a conjugate acid-base pair as well, whereas this is the base. So where this was the acid, this is a base, and this is conjugate acid. This is an acid and its conjugate base. Okay, so same thing. They're very closely related. They're almost identical, but with a difference of one proton. It's just what we see is that this has gained a proton, accepted a proton to become that. Okay, but otherwise, we see these two pairs. So in a Lowry-Bronsted acid-base reaction, we see these two pairs going on. Now, we'll discuss conjugate acid-base pairs in a little bit more detail in a follow-up video. Okay, so that's just kind of a little introduction. Okay, but so what? And then the last concept that we're going to talk about is this idea of substances being amphiprotic. Okay, so what I'll demonstrate for you is this substance, the bicarbonate ion. can undergo two different types of acid-base reactions. Okay, so let's say I combine this with something that's an acid. Bicarb plus an acid. Okay, we're going to get some fizzing. We'll see as one of the things we'd observe, but first of all it starts with this equation. Okay, so what's going to happen is that in this situation it's going to act as a base, and it's going to accept one of these protons that the hydronium is going to donate. So we have one proton more than we did before, and we formed water. So hydronium, to lose that proton, has become water. Okay, so we can look at our conjugate pairs. Here's one. If this is the base, then this is its acid. If this is an acid, then this is its base. But likewise, if I placed it in something that had hydroxide, we'd see something different. What would happen is that it would actually donate one of its protons as an acid to this as a base. And we'd end up with a carbonate ion, CO3 2-, and we'd also end up with water. Okay, so we can again look at our pairs, and so we can see, alright, these are a pair. If this is the acid, it's conjugate base. This is a base, it's conjugate acid. So in this situation we have the same substance being able to both accept and donate a proton. So we say, because it can do both, that it is amphiprotic. Amphi referring to both, and protic referring to protons, or related to protons. So it can both give and receive protons. It can donate or accept protons, depending on what we react with. Now, notice that it's not reacting with the same stuff, that we've reacted them with two different things, but we've ended up with, rather than always behaving as an acid or always as a base, it's been able to do both. Okay, so what we can see, just to quickly recap, because we're almost out of time, seeing that the Lowry-Bronsted theory of acids and bases involve acids being proton donors, bases being proton acceptors. An acid-base reaction is also known as a proton transfer reaction for that reason, because we're taking a proton from one thing and giving it to another thing to make two new substances. We always have two pairs of substances, like two things on the left and on the right, but we can also say that we have related pairs on before and after, and we call them conjugate acid-base pairs. The only difference between them being a proton, and we see that there are some substances, like this bicarbonate ion, that are amphiprotic, are able to both donate and accept protons. Okay, that about covers it for our introduction. Thanks very much for watching. Bye for now.